Today, we're going to pull back the curtain on a force that is silently running pretty much everything, from what's happening inside your body right now to huge industrial processes. We're talking about the invisible balance, equilibrium.
But to kick things off, let me ask you a really direct question. Right now, as you're sitting here, what is it on a really fundamental level that's keeping you alive?
The answer is kind of simple, but it's also incredibly profound. It all comes down to a delicate, invisible balance. A constant, perfectly tuned push and pull happening inside every single one of your cells.
Okay, so where do we find this incredible balance? Well, you don't have to look far at all. In fact, all you have to do is look inside yourself.
Think about this. Every single breath you take is an act of equilibrium. There's this amazing protein in your blood called hemoglobin, and its job is to grab onto oxygen in your lungs. But here's the trick. It can't hold on too tight. It has to be able to let go of that oxygen when it gets to your muscles. This perfect balancing act of grabbing and letting go, that is a chemical equilibrium, and it's what's fueling your every move.
So we know what's happening, but what does this balance actually look like? To see it, we have to shrink ourselves way down to the molecular level and watch what I like to call the invisible dance. Let's start with a really simple example. Just picture a sealed jar with some water in it. If you look at it, it just looks still, right? Totally peaceful. But the truth is, if you could see the molecules, it would be a scene of absolute chaos.
And this brings us to a really important idea. This isn't like a book just sitting on a table. That's static equilibrium. This is dynamic equilibrium. It's a state of perfect balance that's achieved through constant, frantic motion, not through stillness.
So how does this dance work? It's a beautiful two-step. First, you've got these high-energy water molecules that just escape from the liquid and become vapor. That's evaporation. At the exact same time, you've got other vapor molecules that are returning to the liquid. That's condensation. At first, evaporation is happening way faster, but eventually, the two processes match their speeds perfectly. For every single molecule that leaves, another one returns. That's the moment you've reached equilibrium.
And this simple little jar of water shows us all the rules of the game. First, the system has to be closed. You need that lid on so nothing escapes. Second, those two opposite processes, evaporation and condensation, have to be happening at the exact same rate. This creates a state that's both super dynamic and incredibly stable. And it means anything you can measure, like the pressure inside the jar, stays totally constant.
Now, let's take this cool idea of a dynamic dance and see how it applies to something else. It turns out this is the fundamental way chemical reactions find their balance too. You see, a lot of chemical reactions are actually a two-way street. They're reversible. That means they can go forwards, turning reactants into products, and they can also go backwards, with the products breaking down into reactants again. And just like our water molecules, they eventually settle into that perfect state of dynamic equilibrium. So imagine we start a reaction. At the beginning, we have a ton of our ingredients, our reactants. They start combining to make products. So the amount of reactants goes down, and the amount of products goes up. But it doesn't go on forever. At a certain point, the levels of everything just stop changing. They become constant. And that right there is the signal that the system has hit equilibrium.
Now, the reason why this happens is basically a story of two competing reactions. The forward reaction starts out super fast because there are plenty of ingredients to use, but it slows down as they get used up. The reverse reaction starts at zero, but as more and more product gets made, it starts to speed up. Equilibrium is that magic moment when the slowing forward reaction and the speeding up reverse reaction meet and are happening at the exact same rate.
And here is a part of this story that is just wild. Take the reaction for making ammonia. You can start with just the reactants, nitrogen and hydrogen, and let them react. Or you could start in a totally clean container with only the product ammonia and let it decompose. Incredibly, you will end up with the exact same mixture, the same perfect balance of all three chemicals. It's like equilibrium is a destination and the system finds its way there no matter which direction it starts from. So systems naturally want to find this state of balance. But what if we don't want them to? What if we want to interfere? Well, this is where our understanding becomes so powerful because we can actually learn to push the system in the direction we want it to go. The rulebook for this is called Le Chatelier's principle, and it's actually beautiful in its simplicity. It basically says if you have a system at equilibrium and you stress it out, change the concentration or the pressure, the system is going to fight back. It will shift its balance to try and undo whatever you just did. Let's see this in action. Imagine a reaction is just happily sitting at equilibrium. Let's introduce a stress. We're going to dump in a whole bunch of extra reactant.
So what does the system do? It's going to try and get rid of what we just added. And the only way to do that is to put the forward reaction into overdrive. It consumes that extra reactant, and in the process, it churns out more product. We pushed it, and it rebalanced itself by shifting forward. Okay, let's try another one. This time we've got a reaction with gases, and we're gonna apply a different kind of stress. We're gonna crank up the pressure by squishing the container.
Now the system feels that increased pressure, and it wants to relieve it. And how can it do that? By reducing the number of gas particles that are bouncing around. So the equilibrium will shift to favor the side of the reaction that produces fewer molecules of gas. It's a really clever way of making more room for itself to ease that pressure.
And this ability to push and pull on a system, this brings us to the really big picture. Understanding this whole intricate dance and knowing how to influence it is how we control the outcome of countless processes that shape our modern world.
So, the most important thing to remember here is that equilibrium is never a static endpoint. It's not a finish line. It is a continuous, dynamic dance that's happening all around us and inside of us every single moment.
And knowing the steps to this dance is just so important. In industry, it lets chemists get the most product they can out of a reaction. In our bodies, it's the very thing that keeps us alive. And in environmental science, it helps us predict how our planet is going to respond to change.
Which really leaves us with one final thought. In chemistry, in biology, in physics, it seems like every system, when it gets disturbed, works tirelessly to find a new state of balance. So if nature itself always seeks equilibrium, what can we learn from it?